Vær så god.
Hello. Jeg skal snakke på engelsk. Ja. Skal jeg se I kamera? Eller er ikke det? Nei. Hello, my name is Ingelin, and I'm going to present my project work, which has the title Design Optimization of Francis Turbine Draft Tube. And the objective for my work is design and optimization of a high-head Francis turbine for variable speed turbine operation. Focus will be steady-state operating condition of the turbine. And this project work and also master work is connected to the project Hydroflex, which is an ongoing research project at the hydropower laboratory. And it's about developing more flexible operation for Francis turbine. So this is an overview of the work I've done this far. I have been studying theory about draft tube design and also theory related to optimization methods. And I also dived into some software knowledge. I learned about ANSYS, CFX simulation tool. And I have also done a couple of simulations this autumn and evaluated the results. So first of all, this is a hydropower plant, and the draft tube is located after the runner. It's the pipe which is leading the water from the outlet of the runner into the tailwater. And why do we need draft tubes? Well, the main task is for a draft tube is to convert kinetic energy at the outlet of the runner into pressure energy at the outlet of the draft tube. And the draft tube design has developed a bit over the years. The first draft tube was just a straight diffuser, and then the bell mouth draft tube, the number B, was invented. And today, most of the draft tube designs for Francis turbines are bent draft tubes. This enables possibility to have a bigger runner diameter, but the bend in the draft tube also cause a more complex flow and also pressure loss. So this is this diagram is showing the energy conversion in a Francis turbine, and the reason why we need it is because the draft tube is increasing the efficiency of the runner, because the area, can you see this one? Yeah, this area here is related to the transferred energy from the water to the shaft of the runner. And if we don't have the draft tube, only this area will be transferred, because then the pressure at the outlet of the runner will be fixed by the tailwater. Yeah, so how can we measure the efficiency of a draft tube? We have two important parameters. One is the pressure recovery factor, which is a non-dimensional size, which is looking at how much has the pressure increased through the draft tube. And we also have the energy loss coefficient, which is looking at how much has the total pressure, the stagnation pressure, decreased through the draft tube. The pressure recovery factor is used a lot for experimental draft tube design as well, but the energy loss coefficient is really hard to use for experimental design, because then you need to know the velocity at the whole inlet of the draft tube and also at the outlet of the draft tube. But when you do CFD analysis, this is possible, because then you have all the data you need. This is a chart showing the main the flow in the process of doing surrogate model optimization. And surrogate model optimization is like a wide branch of different optimization techniques, and which I will use for my master work. And it's about, you first need to parameterize a draft tube in terms of have different parameters describing the geometry. Then you choose some different operation points for flow rate and as well for the parameters where you are going to do some CFD analysis. And then you will obtain some results. And then the whole clue about surrogate optimization methods is to create a mathematical function which is describing how parameters such as the pressure recovery factor and the energy loss coefficients is varying for different design variables. And there are several ways to do this. Response surface model is one very common way to do it, which is using root mean square to obtain a mathematical model. And we also have a lot of machine learning algorithms which also can be used. So this is what I plan to do for the spring semester. Here you can see some typical parameters you can have of a draft tube. And the rule of thumb is that the more parameters you choose to describe a draft tube, the more complex will the analysis be. But also maybe give you more reasonable results. So this is moreover to what I have done in ANSYS this semester. I have used the first model is a surface model from the Francis 99 project, which is just lines describing the surface of a draft tube, and have been used this draft tube design to try to create my own draft tube volume. So I've never been CADing before, so I've explored like different ways to transfer this just surfaces into a volume, which turned out to be pretty hard. But the final way I figured out to do it was to just construct a few cross-section surface of the draft tube, and then draw lines, polynomial lines, and then use a blend tool to create a volume. So the last picture is showing the final draft tube I've been used for my simulation. I have also learned about meshing, and my main, this is actually what I used the whole October month for, which was a failed meshing attempt, where I tried to construct a O-grid mesh, because that will give low CPU time for a good mesh resolution. So what I tried to do then was to have very many cross-section that I transfer into volumes, and inside every cross-section I created a square prism. So I was able to like control the number of divisions when I used the meshing tool. And that turned out to be very manual work. And worst of all, it's not scalable. So I will not be able to use this approach for doing design optimization. But I learned to use the number of division tool in ANSYS meshing at least. So this is the final mesh I obtained, where I used the green one, this geometry, and it's a more automatic meshing method. And you can see it's the picture to the right is showing the outlet, so it's not like a O-grid mesh, but my co-advisor Chirag told me that it will be okay for my simulations. And I've also used an inflation layer method at the walls of the draft tube, because that's where the boundary layer will develop, and it's important to have very fine mesh grids there. Yes. So I've done a couple of simulations. I used some data from a full turbine simulation, and I specified the velocity at the inlet. I used the outlet as an open boundary, and I had also a little cone at the top of the turbine, which is rotating, which is representing the downer surface of the turbine. And I first did some steady-state simulation, which I used as an initial condition for transient simulation. This is some results. It shows the pressure recovery factor, and I did a simulation for different guide vanes openings, so for different part load, design load, and full load cases. And the 10 degree of a guide vanes opening is where you have the best efficiency point. So it's actually it's turned out that the pressure recovery factor is much better for lower flow rates. And this is the energy loss coefficient, which you want to keep as low as possible. So that one is very low for 10 degrees, which is great. And further work for my master thesis will be to choose parameters for my parameterization, create the geometry and a scalable mesh, choose some operation points, one part load, one design load, and one fully load, which I want to optimize the geometry for, and choose optimization method, and then try to do some validation and verification of the results. Thank you.
Thank you.